I need a haircut pretty badly, but you know what? It's fine. Let's talk about equations for planes. So, find an equation for a plane normal to the vector n is equal to 2, 3, 6. So, when you're thinking about these kind of problems, draw out your coordinate system and draw the vector, right? Just to get an idea of, I guess once you know how to do it, you don't need to do it, but when you draw the vector, it becomes pretty clear how to go about doing this. So 2, 3, 6, you don't need to get it perfectly, but now this normal vector is important, and it's saying find an equation for a plane normal to the vector 2, 3, 6. Well, guess what? You remember, vectors are not defined by their starting points, endpoints. You can draw this vector anywhere. So that means there's really, like, if you think about a plane, like normal to this vector. So let me draw this kind of a plane, right? So if you think about a vector, I guess we could kind of draw it like this, right? If you think about it, normal to the plane, like so, I mean, you can draw this vector anywhere. So this plane could be anywhere in space. That's why it's saying find an equation for this vector. So here's how you go about doing this, right? If you think about a point P on this plane, let's say there's a point P right here, where it's X, Y, Z. So this could be like any point on this plane. But in order for this point to be on this plane, if you were to draw a vector from the starting point of N, which in this case is the origin, you will see that, hey, these two vectors have to be perpendicular. Hopefully that makes sense, right? Like if N is normal to the plane and point P is on the plane, if you were to draw a vector from the origin to point P, it's going to be perpendicular to N, which we already have a definition it's 2, 3, 6. So we just need to find a vector, or we just need to find essentially the dot product, right, of N and this vector. We'll call this vector P. And if the dot product ends up equaling 0, that means the two vectors are perpendicular, and we're going to get a general case for all the points X, Y, Z that will exist on this plane, right? Because let's just start doing that process. If you think about, point P dot N is going to equal, should equal 0. So if you're doing X, Y, Z dot 2, 3, 6, it's going to equal 0. And because we're not doing actual numbers like X, Y, Z, this will just give us a general equation for a plane where I'll show you what I mean. If you're doing the dot product, it's essentially 2x plus 3y plus 6z equals 0. That's our general equation for the plane, right? Because X, Y, and Z are just general, it's just a point on that plane. This holds true for any point on the plane. That's kind of the idea. So now let's see what happens if we need to introduce another kind of condition. Well, yeah, I guess condition you can call it. What happens if the plane has to pass through a certain point? So now find the equation the equation for a plane normal to vector, same vector, and contains point P is equal to, let's just say 4. Should we do 4, -2, 1 maybe? It's a random point. So yeah, now we have this point that it needs to pass through. So if you think about, I don't know why I erased it. I was going to need to redraw it again. So if you think about this little coordinate system thing, our last X, there we go. Our last plane passed through the origin. So it kind of looked like this. Well, maybe not this exact slant, but it passed through the origin. Now we need to find a plane that passes through the point given, 4, -2, 1. So if we draw in that point 4, -2, 1, it would be kind of like right here. So we need to have it pass through that point. Well, we can do the same similar kind of process, right? If you think about the normal vector 2, 3, 6, right? If this is vector n and this will be our plane, then the same thing kind of holds, right? If this is point P initial and we have a point P right here, then the vector from P initial to P dot n would have to equal 0, right? So same process, right? So if I say the vector from P initial to P dot n is equal to 0, what is P initial to P? Well, let's say P, point P, and point P as in that P, is at our x, y, z, like our general point on the plane, then that vector is just going to be x minus the x component, or not the x component, but the x coordinate of P initial, right? So it would be x minus 4, and then it would be y minus the y coordinate of P initial -2, so y plus 2. And hopefully that makes sense, right? Because in order to get from P initial to P, you have to go x, and then you have to go y, and then you have to go z in terms of the vector components from point P. So if you work backwards, that is the vector you would get. So, or yeah, I should say, to get to point X, you don't go X, sorry, because this is X from the origin, my fault. You would go 4, and you would go 4x, 2 to the left, that kind of thing. Hopefully you get what I mean. Hopefully that kind of makes sense. You're just kind of going backwards. Dot n, which we said was 2, 3, 6, which is going to equal 0. So this is the dot product we're taking, and it's the same process, right? 2 times x minus 4. Plus 3 times y plus 2. Plus 6 z minus 1 is an equal 0. Or 2x minus 8 plus 3y plus 6 plus 12. Oh, I was going to read this as a 2. 6z minus 6 equals 0. Take your constants on the other side. -8 plus 6 is -2. -2 minus 6 is -8. And you get 2x plus 3y plus 6z equals 8. Assuming I didn't make any mistakes along the way. So you can see that this portion of the equation, right, that was the same as before when we had the 2x plus 3y plus 6 equals 0. So, and that kind of makes sense, right? This kind of determines, this part of the equation kind of determines the slant of the plane, because this stuff is what makes it normal to the vector 2, 3, 6, right? Like this 2, 3, 6, that is what kind of determines that's what makes a plane perpendicular to that vector. So it's really the same plane as the last time, but this 8 shifts our plane elsewhere. So yeah, the ax, by, c, z, right? The a, b, and c controls the slant, or making it perpendicular to the normal vector, and then the d, or the 8, makes it shift around. So in general, the equation of a line, so equation of a line, or plane, plane is going to be ax plus by plus cz is equal to d. So there you go. That's the equation of a plane. Let's do one last example this time. And this time we're going to look at finding a plane that passes through 3 points. So we want to find a plane that passes through point P1, which is going to equal, let's just have it equal, I did an example right here, 3, 4, 1. Oh, 3, 4, 1. Let's have P2 equal 5, -3, 4. And then let's have P3 equal 8, 0, 6. Okay, so we need to find an equation of a plane that passes through these 3 points. Keep in mind, the third point is important. I can't really find, I could find an equation for a plane of P1 and P2 because there's infinitely many. There's an infinitely many amount of planes that would be going through P1 and P2. I mean, think about it. If my fingers are the 2 points, right, that just exist somewhere in space, I could do a plane here, 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 here. I could do a plane like here, here. But as soon as I introduce that third point with being my thumb, I really only get a plane like so or like so, right? I can't really go like this or like that. I need to include all 3. So if we think about, let me just get a new coordinate system here because you know me. If you think about drawing these 3 points in, so z, y, x, you're gonna have point P1 right here, P1. And then you will have P2 right here. And you will have, I don't know, P3 like maybe right here, right? So, I'll draw, even though it's not probably realistic, I'll just draw P3 right here. So I need a plane containing all of these points. Now, here's the deal, right? This plane is still going to be normal to some vector n, right? It's still going to be normal to a vector. I just don't know what the vector is. It could be any vector in the world. So when I'm doing my old strategy of let's start at P1 and let's go to a point P that has coordinates x, y, 0, it's just harder because when I'm taking the dot product of, let's do like P1 and P, right? When I'm taking that dot product, I just don't know what n is. So I can't really compute this out. So I just need to find out what is that normal vector, right? Well, hey, what's a normal vector that I could make with these points in mind? Well, if I create vectors from point P1 to P2 and then from point P1 to P3, this normal vector could just be the cross product of P1, P2, and P1 to P3, right? Because cross products are always perpendicular to the 2 vectors that cross product. To create that cross product, you know what I mean? The result is always perpendicular. So I could say that, well, I can just do P1, P2 cross P1, P3, and that's going to equal, I'm going to do my determinant stuff. First, I'm just going to quickly define P1 and P2. So P1, P2 is going to equal 5 minus 3. So that's 2. Negative 3, is that a... Oh yeah, no. Negative 3 minus 4, which is negative 7. And then 4 minus 1, which is 3. And I'm just going from P1 to P2. So I just subtract to find the actual vector. I'm so sorry. These are points, not even vectors. I am so sorry. Oh my God. I really hope, if anyone noticed that, I hope you watched through to watch me catch that mistake. Okay, and then these are vectors. P1, P3. It's 8 minus 3, which is 5, and then 0 minus 4, which is negative 4, and then 6 minus 1, which is 5. So these are my 2 vectors stemming from P1. So now I can fill in my determinant. I hat, j hat, k hat, 2, negative 7, 3, and then 5, negative 4, 5. So to find a cross product, right, you cover up the I, find that determinant, and then do that process. So you really get, I'll make a video on cross products one day, hopefully. So it would end up being, negative 7 times 5, negative 35. Oh, I messed up somewhere, didn't I? No, I didn't. I know, I'm good. Wait, I did. Where the hell did I mess up? I checked my answer on Desmos. This is right. 100%. That's so weird. I had the right answer. Oh, maybe I just didn't get the right answer. What the heck? Okay, well, maybe this is not the right answer. Maybe I don't know. If I'm making a mistake, someone catch me. Negative 35 plus 12 I hat. I guess I don't really have to do the I hat, right? I can just kind of do it in vector form already. So it's going to be negative 7 times 5 plus 12. So negative 35 plus 12 is 23. So negative 23. And then we're going to do 2 times 5 minus 3 times 5. So that would be negative 5. But then you make it negative, so it would be 5. And then we're going to do 2 times negative 4, which is negative 8, plus 35. So 35 minus 8 would be 27. So that is going to be that normal vector, right? Obviously, like, this normal vector could be of any magnitude, but if I would just need a vector in a pinch that's perpendicular, hey, I can just do the cross product. But, it could be a unit vector for all I know. Doesn't really matter. I can decide that this is the normal vector because it's actually normal. So P1 to P, let's do this. So this P1 to P would just be x minus 3, y minus 4, z minus 1, dot, now negative 23, 5, 27. It's all going to equal 0. So negative 23, oh boy, x minus 3 plus 5, y minus 4, plus 27, x minus 1. It's all going to equal 0. Let's distribute. So negative 23x plus 69, I think. That seems right. Plus 5y minus 20 plus 27x minus 27, which is going to equal 0. So 69, so I guess I should do this part, negative 20. So that would be negative 47. 69 minus 47 would be 22. So the answer would be negative 23x plus 5y plus 27. I wrote an x there. I'm sorry, 27z. Going to equal negative 22. I will check my answer on Desmos and I will make corrections if need be. I think this should be right though. Definitely more right than my work I had going on here. Thank you for watching. Hopefully you got something out of this. Yeah, there you go.